And the next presentation will be delivered by Team Marvis with the title Proposal for the Standardization of AI Deep Learning-Based Tracking Technology in SOLAS to Address Maritime Blind Spot. Please welcome the team with a big round of applause. And we are going to watch the introduction video before the presentation.
넓은 바다 위 보이지 않는 위험은 언제나 존재합니다. 마비스 머린 비전. 우리는 선박의 사각지대를 없애기 위해 딥러닝 기반 객체 인식 시스템을 제안합니다. 바다를 더 안전하게, 시야를 더 넓게. 팀 마비스.
Good morning, ladies and gentlemen. This is Team Marvis, and we are here to propose a standardization of AI deep learning-based tracking technologies in SOLAS to address maritime blind spots. You know, this is our index. We first talk about blind spots problem and IMO's reaction and accident case, and we will explain about AI deep learning technology, and next about SOLAS. When it comes to keeping big ships safe, we mostly rely on AIS and radar, but there are some real problems. AIS can be spoofed if a boat doesn't have AIS, it's basically invisible. Plus, with all the cargoes stacked up on a huge ships, radar can just see everything. Especially close by, where sea clutter makes things even worse. The IMOs has been talking about this for a while. In this document, they actually called out the need for extra watchkeeping in radar blind spots and pointed out that small, fast boats are tough to detect. They have recommended extra coverage at the stern and more backup systems. This is an example. Back in 2022, near Vancouver, a boat carrier, Saiga Beija 4, collided with a small leisure boat. This little boat was sitting right in the ship's blind spot. The radar couldn't pick it up, and it didn't have AIS. It's a classic case that is showing our current systems and just keeping watch with our own eyes are not enough to spot small and nearby targets. To address these technical challenges, ship object recognition systems based on deep learning provide a concrete solution where traditional sensors are limited. These systems use cameras or optical sensors in blind spot or vulnerable areas of vessels to constantly feed real-time video into onboard computing units. The captured imagery undergoes pre-processing to reduce noise and optimize brightness and contrast for maximum clarity. Next, advanced deep learning models, typically convolutional neural networks such as YOLO or faster RCNN. They analyze each video frame, extracting features and scanning for possible ship and hazard objects. Methods like non-maximum suppression are used to resolve overlapping detections, while newer developments enable pixel-level segmentations for highly precise boundary definition. Multi-object tracking algorithms are often integrated to maintain accurate and consistent detection results even as object moves. Once identified, objects are visualized in real time as colored boxes or overlays or symbolic markers on the bridge display, providing immediate and actionable information about potential collision risks. This fully automated process, and with processing latency below 100 milliseconds, greatly improves situational awareness and safety, especially for small, low-profile vessels in close proximity or otherwise lost in radar blind spots.
But if you look at SOLA's Chapter 5 regulations, it's still all about the old school gear that like radar, AIS, ACTIS. There is nothing in there about vision-based detection systems. No standards for how they perform, be tested, or share data. That's a big gap. So here's what needs to change. First, SOLAS 519 should get a new clause for blind spot visual detection system. Any cargo ship with 5,000 gross tonnage with a bow or stern blind sector bigger than 10 meters should have a certified vision-based detection system. It should give a real-time alerts and overlays on the bridge display and follow an approved maritime data model. Second, we need a separate resolution that spells out exactly what we expected, at least 95% detection accuracy in daylight, 90% in night, less than 2% false alarms. Under 100 milliseconds of processing delay, able to spot a 2-meter target at 100 meters, a detection range of 50 to 2,000 meters, and system uptime of at least 99.5%. Testing should mix real-world scenarios, displayed video datasets, and simulators, covering different sea states and visibility. The bridge display should use clear symbols, colors, and smart alarm logic to avoid overwhelming the crew. We also need rules for cybersecurity, model updates, and making sure the system keeps working well over time. And of course, the data should be standardized so it works with ACTIS overlays. Rolling this out should happen in stages, voluntary pilots and early adopters from 2026 to 2029. Then new ships get the mandate from 2030 to 2035, and after a grace period, all ships have to comply by 2040. Every steps, we should have an international groups, flag states, industries, insurers, VTS, reviewing real-world results and updating the guidelines. If other sensor setups like thermal cameras can hit the same safety goals, they should be allowed to. This approach puts IMO recommendation into action, fill the gaps in radar coverage, and gives us a practical way to prevent accidents like one in Vancouver. It's realistic, it's doable, and it's what we need to make shipping safer for everyone. Thank you for listening.
Thank you very much for the presentation. Now it's time for Q&A. Judges, please proceed with the questions. Yes, please. With your microphone, please.
Thank you for your presentation. It's very good ideas and suggestions to identifying about the blind sector. But I think, in my opinion, I think there is not close connection between the blind sector in your presentation only. AI deep learning. We mean AI deep learning is the learning like human beings, isn't it? From the big data. But in here, you mentioned just processing the images to the processed by CNN independent deep models. Can you explain more about the connectivity between the blind sector and AI deep learning?
Thank you for your question. RCNA is a region-based convolution neural network and a deep learning method for image object recognition that extract and classify specific regions within images, now applied to automatic vessel identification and maritime camera analysis. We use this RNN or CNN to AI, so they learn about images and detect vessels from video. Thank you.
Let me continue with the answer. There's some problems when we just keep watch with our own eyes. Sometimes we miss some objects and a little shapes that can be happen. And if there's like little boat comes into a blind sector, we cannot detect them, and that can be connected to a collision. So that's why we propose this blind sector sensor for detecting not only just little boats, but also not only like fishing boats and some floating things such as buoys.
Did it answer your question, Secretary General? Okay, thank you. Yes, please.
Good morning, everyone. Thank you for your valuable presentations. As a pilot, blind spot is the biggest problem when the berthing or unberthing. So, how can your proposed AI-based detection system maintain accuracy under harsh maritime conditions such as fog or low visibility? How can?
Thank you for your question. Environmental factors like waves, rain, and fog, and glare, they can be a major challenges for vision-based systems. To address this situation, we made 3 options. First, thermal and infrared cameras should be installed alongside optical sensors to maintain detections in low visibility or nighttime conditions. And second, image pre-processing should include contrast enhancement and noise reduction and dehazing algorithms.
And some multi-sensor fusion, like radar AIS vision should be used to compensate for individual sensor weakness. Additionally, deep learning models must be trained on data sets covering a wide range of weather and lighting conditions to ensure robustness. Thank you.
You can use the rest of the time for the final comments.
Another questions. My concern is cost. You said that the YOLO and faster RCN and this kind of model need a lot of requires more money for the. You need a lot of computational power and infrastructure, but how can we solve this concern?
Mr. Park, I'm so sorry we are out of the time. I'm so sorry we don't have the time for the answer. So I guess that's the end of the Team Marvis. Thank you very much for your presentation. Please return to your seat.
Thank you very much.
Thank you.